Welcome to our presentation on Bayesian time-varying coefficients VAR models. This comprehensive guide is tailored for university students, graduate researchers, and econometricians. We will delve into both the underlying theory of these advanced models and their practical implementation using EViews. As the quote on the slide emphasizes, the only constant in economics is change. This fundamental principle drives the need for models that can capture evolving economic relationships, which is precisely what time-varying coefficient VAR models allow us to do. Standard models like the vector autoregression, or VAR, assume a static view. They fit a single relationship with a fixed coefficient, let's call it beta, across the entire dataset. In contrast, the dynamic view, embodied by the Bayesian time-varying coefficient VAR, or BTVCVAR, allows the coefficient, beta t, to evolve over time. Economic reality is not static. Major events like policy shifts, financial crises, or even gradual changes in consumer behavior can alter underlying economic relationships. Models with constant parameters fail to account for these structural breaks, which often leads to inaccurate conclusions and poor forecasts. When you have time series data, the first question is about stationarity. If your data is non-stationary but co-integrated, you should consider a vector error correction model, or VECM. If the data is stationary, the next question is whether the model's parameters are constant. If they are, a standard VAR is appropriate. If parameters are not constant, we must determine the nature of the change. For abrupt, discrete shifts, like those caused by a war or a sudden policy change, a switching VAR is suitable. However, for gradual, smooth evolutions, such as a central bank slowly adopting an inflation targeting policy, the TVCVAR or BTVCVAR is the superior choice. This decision rule emphasizes using switching VAR for abrupt events like wars or instant policy changes, and BTVCVAR for evolving behaviors, such as gradual inflation targeting. A classical or frequentist time-varying coefficient VAR often suffers from over-parameterization. Estimating a different coefficient for each variable at each point in time creates high uncertainty, leading to noisy and unstable results. The Bayesian approach solves this problem using priors. A prior is information we provide the model about what the coefficients might look like before it sees the data. This process induces shrinkage. The model pulls the estimated coefficients away from extreme, wild values and shrinks them toward a more central, simpler model defined by the prior. This is especially crucial when data is limited. The result is a more stable and reliable set of time-varying parameters, preventing the model from fitting noise in the data. Think of it like this. Without a prior, the model is like a student with no textbook, trying to learn from random examples. It might get confused by outliers. A prior is like giving the student a textbook. It provides a solid foundation, guiding the learning process toward a more sensible conclusion. This concept of priors and shrinkage is implemented through a specific mathematical structure. Let's now look at the core equations that define the model. The BTVCVAR is elegantly represented in a state space form, which consists of two key equations. The first is the observation equation, yt equals xt beta t plus epsilon t. This looks like a standard regression, but the crucial difference is the time subscript t on the coefficient vector beta t. This means the relationship between our variables yt and xt can be different at every point in time. The second is the transition equation, beta t equals beta t minus 1 plus vt. This equation governs how the coefficients evolve. It specifies that today's coefficient, beta t, is simply yesterday's coefficient, beta t minus 1, plus a small random shock, vt. This is known as a random walk assumption. Together, these equations allow us to estimate a path for the coefficients, assuming that they change slowly and smoothly over time, rather than jumping around randomly. The primary output of a BTVCVAR is a plot of each coefficient over time. like the one shown here for the effect of interest rates on inflation. A traditional static model would give you a single horizontal line, the average effect over the whole period. For example, a 1% rise in rates decreases inflation by 0.5%. The dynamic view, however, tells a much richer story. We can see that the policy effect was weak in the 1970s, but became much stronger in the 1990s. The shaded area represents the confidence bands. A key rule for interpretation is that if these bands do not include zero at a specific point in time, the relationship is considered statistically significant at that moment. To begin in EViews, the navigation path is straightforward. Go to the main menu, select Quick, and then Estimate VAR. This will open the VAR specification dialog box. In the VAR type drop-down menu, you must select Bayesian TVCVAR. The dialog box has three important tabs: Basics, Prior, and Options. A pro tip for starting out is to use a conservative lag length, such as 1 or 2. This helps preserve degrees of freedom, which is important in these parameter-heavy models. You can also use the shortcut by typing VAR in the command window to open the dialog. This slide details how to configure the priors within EViews, specifically in the Prior Specification tab of the VAR dialog. We have mu1 under coefficient priors, which sets the AR1 mean. For example, a value of 0 suggests the variable is not persistent. Under residual priors, lambda1 is a critical parameter that controls the overall tightness of the prior. A smaller value, such as 0.1, imposes stronger shrinkage, pulling coefficients more aggressively towards the prior mean. An essential feature is the prior sample, shown here as 1970 Q1, 1980 Q4. This acts as a training wheels period, allowing you to use a subset of your data to establish a baseline for the priors before the model starts learning from the main estimation sample. It's important to note, as highlighted on the right side of the slide, that lags must be contiguous in the BTVCVAR specification within EViews, for example 1-2 rather than 1-3. These settings are crucial for achieving stable and meaningful results. For our case study, we will replicate the analysis of Chan and Gelyazkov 2009 on U.S. macroeconomic dynamics. The objective is to analyze how the transmission of monetary policy changed over time, particularly during the period known as the Great Moderation, when economic volatility decreased. The dataset spans from 1948 to 2009 and includes variables like GDP growth, the unemployment rate, inflation, and the federal funds rate. Before estimation, it is essential to ensure all data are stationary. This might require transformations like taking first differences for variables that have a unit root. This is the EViews command to estimate our BTVCVAR model. Let's break it down. Nu1 and Nu2 are hyperparameters for the prior distribution, controlling its shape and tightness. Size equals 20,000 specifies the number of draws to generate from the posterior distribution using a technique called MCMC, Markov Chain Monte Carlo. A higher number leads to more accurate estimates but takes longer to run. Burn equals 1,000 sets the burn-in or warm-up pyramid. The initial draws of the simulation can be biased by the starting values, so we discard the first 1,000 to ensure the results reflect the true posterior distribution. Use mean tells EViews to use the mean of the posterior draws as the final point estimate for the coefficients. The command var myvar.btvcvr, size equals 20,000, burn equals 1,000, 1 GDP on EMP interest inflation creates a BTVCVR object named myvar with one lag for the four specified variables, running 20,000 iterations and discarding the first 1,000. Once the command is executed and the estimation is complete, EViews will generate an output object. Let's see how to interpret it. The output of a BTVCVAR estimation is not a simple table, but a collection of objects called a spool. The summary view shows the average posterior coefficients over the entire sample, which can be a useful starting point, but misses the main story. The real power comes from visualization. Don't just look at the numbers. You should click on the Graphs node in the spool object tree. This will generate plots of the time-varying coefficients, allowing you to visually analyze their trends. You can see if a coefficient is rising, falling, or stable over your sample period, which is the key insight from this model. A standard VAR produces a single impulse response function, or IRF, as shown in Chart A. It shows the average response of one variable to a shock in another over the entire sample. A BTVCVAR, however, can generate time-varying IRFs, as seen in Chart B. This allows us to see how the system's response to a shock has changed at different points in time, specifically showing impulse responses for 1975, 1990, and 2005. This highlights a critical takeaway: context matters. The economic system is not static, and its response to shocks evolves. For example, a monetary policy shock, an unexpected interest rate hike, in 1975 might have had a very different impact on unemployment than the exact same shock would have in 2005, and the BTVCVAR is designed to capture this evolution. The EViews command, myvar.impulse, CE equals Bayes, horizons equals 59, show CI, GDP unemploy, is used to generate these time-varying IRFs. Since Bayesian estimation is a simulation, it is crucial to always check convergence diagnostics before publishing your results. A key diagnostic tool is the inefficiency factor. As you can see in the table, a high inefficiency factor, particularly a value greater than 20, like the 25.0 for C21, indicates poor mixing. This means the simulation might not have adequately explored the parameter space, leading to unreliable results. If you encounter high inefficiency factors, the solution is to increase the number of simulation draws, which is the size option in EViews, or extend the burn-in or warm-up period, and then rerun your estimation. The EViews command, proc make inefficiency factors, will generate this table for you. Here is a quick reference for the main commands. For estimation, you use the varname.btvcar command with your options, lags, and variables. To generate impulse responses, you use the name.impulse procedure on your estimated VAR object. If you need to analyze the simulation results in more detail, you can extract the posterior draws using the name.proc put posterior draws command. And finally, for the crucial diagnostic step, you use name.proc make inefficiency factors to check for convergence. Using these commands from the command line is especially powerful for batch processing, allowing you to automate the testing of different models and prior specifications in a loop. BTVAR bridges the gap between rigid theory and the fluid reality of economic data. Thank you. For further reading, we recommend Chan, J.C.C., and Jelyaskov, I., 2009. Efficient Bayesian Inference for Multiple Change Point and Mixture Innovation Models, Journal of